So the main thing we're going to use the law of sines, and we'll see later in 6.2 the law of cosines for, is solving these triangles. That is, being able to find the other measurements given some selection of them, where the law of sines is generally used to solve what are called angle, side, angle, or side, angle, angle arrangements. That is, arrangements where we know the two angles adjacent to one side, or a pair of any two angles, and a side where they are not necessarily all adjacent to each other. So, to understand this, we're going to look at a couple of examples. So for our first example, we want to solve the given triangle where we'll notice this is not a right triangle, and we have two angle measurements and one side measurement, where in particular we have an angle opposite and an angle adjacent to the side. That 82 degrees is opposite, that 64 degrees is adjacent. So we can think of this as a side angle angle, as it were, sort of coming around almost. But here we have that amount of information. We want to get the rest of our information. So the first thing we want to do here is take what we have in terms of our angle measures and use that to get that third angle B that we don't know anything about. Because once we have our three angles, we can then use the law of sines to turn those around and get our other two side lengths. So we're going to use one of those defining, that's what I'm looking for, relationships, I guess, for any triangle, that the sum of the angle measures is 180 degrees, or if you prefer pi radians, we're going to use degrees a lot in this section in particular. But we have those, and in this case we have the angles A and C. That is, we must have 64 degrees plus B's measurement plus 82 degrees equals 180 degrees. And what we can do is take this 64, pull it over there, take the 82, pull it over there, that is, subtract both, and get that B must be equal to 34 degrees. And from here, since we have all of our degree measurements, we can use some rearrangement with our law of sines to get the lengths little a and little b, as it were, because, as we know, we have a over sine of a equals c over sine of c. But, in particular, we know that c is 14 centimeters, but I'm not going to worry about that unit for now. And big C, the angle, is 82 degrees. And technically speaking, we actually didn't need to find B before we did this, but usually it's good to just be sure. Be sure, ha ha ha. Anyway, we also have on the other side that, well, A is unknown, so we're trying to find, but big A, the angle, is 64 degrees. So we can say that the side length, little a, is equal to that value here multiplied by sine of 64 degrees. That is, a is equal to 14 times sine of 64 degrees divided by sine of 82 degrees. Which, if you plug that into a calculator, there's going to be a lot of calculator plugging in here. I'm not going to show you how to do that again because, well, it's just plugging numbers in. It's not that exciting. But you do that and we'll get the value here is approximately 12.7 centimeters. That is, side A is about 12.7 centimeters long. Similarly, if we change this relationship and talk about B over sine of B, we get the exact same thing. As a result, I'm not going to copy down all of the work because it's the exact same work and I don't have a lot of space. we could say that B is equal to C times sine of B over sine of C, or if we prefer, B is equal to A sine of B over sine of C. It works the exact same way. But I'm doing it this way just to match with consistency for no good reason. We have 14 sine of 34 degrees from that computation we did up there, divided by sine of 82 degrees again, which in this case will give an approximate value of 7.9 centimeters. So our goal when we're solving a triangle is use the information we have, get all of our angle measurements, get all of our side lengths. In this case, to me, it makes sense to find all the angle measurements first because we got 2 of them, and then use what we have with the law of sines. Once we have the angles, all we need are sides. We usually have at least one to pull our pieces around. And we're going to see that in the next example, it works kind of the same way, even if we change the arrangement, which I think it's fair to wonder that it should work that same way, because we still have 2 sides, or excuse me, 2 angles and a side. How different could it possibly be? We'll see that in the next case it really isn't that much.